In much of chemistry, we're dealing with measured numbers, which are quantitative observations or estimations of the value of a property of matter. It always involves some level of uncertainty, and this needs to be appreciated as we use these measured numbers in calculations. The reliability of a measurement depends on the measuring device and the skill of the operator. For example, if we look at this bar that we can measure with two different measuring devices, the first has the division. Each division is 1 centimeter, represents 1 centimeter in length, and the second one, each division is 0.1 centimeters. When we obtain a measurement, we need to read between the lines, i.e. estimate to the nearest 1/10 of the space between the divisions. For example, this bar measured by this ruler is somewhere between 5 and 6 centimeters. We can estimate that this is about, let's say about 5.4 centimeters. The 5 is a number we're certain of. This 4 is an estimate of how far that value is between the smallest divisions. And since the smallest divisions here are 1 centimeter, we estimate to the tenths of a centimeter. In this ruler, using this ruler, each division is 0.1 centimeters, so we can get a more precise, a more reliable value, and we can see that it's somewhere between 5.3 and 5.4 centimeters, and we can estimate that it's about, let's say, 60% of the way between, so we could give a value of 5.36 centimeters. In this case, it's the 6 that is the estimated value. So this ruler can give us a more reliable measurement of the actual length of this bar and is therefore expressed using more significant figures. Some more illustrations. If we look at this piece of wood, each division here is 1 centimeter, so our measurement might be, 4.5 centimeters. And again, it's this last significant figure that is uncertain because it is estimated. The wooden bar measured using this ruler here, we see that each division is 0.1 centimeters. So when we read between the lines, we see that it's somewhere between 4.5 and 4.6 centimeters. Let's say 4.56 centimeters in distance. And it's the 6, this last sig fig, that is our estimated value. So if we were to use either of these values in a calculation, we would treat this value, 4.5 centimeters, as less reliable. Looking at the penny, we see each division here is 1/10 of a centimeter. So if we read between the line, we're going to be reading plus or minus 0.01 here in the hundredths place. So we're going to be estimating to the hundredths place. It's just shy of 2 centimeters. Let's say somewhere about 1.92 centimeters, but certainly some measurement that's going to be close to that that is given out to the hundredths place. So that corresponds to choice C. To measure the volume of water, the same principle is involved. We're going to read between the lines. Here we can see that each line corresponds to a millimeter. Alright, we have a blow up to the right here of the actual point where the meniscus is. And if we look straight across, you see it's pretty much almost exactly on this line, which is, this is 65, 66, 67, 68, maybe 68.0 milliliters or 68.1 maybe milliliters. Either one of those I could envision being a correct value, and matching up only with choice C. Related to measurement are the terms of accuracy and precision. Accuracy gives you some indication of how close that measurement is to the true or accepted value. And precision is the closeness of multiple measurements to each other. Now there's some difference in how people would interpret this first figure. On average, if we took an average of these values, it could be said that this is an accurate set of measurements. However, we really don't have time typically for multiple measurements, so I would argue that this cartoon represents measurements that are not accurate and not precise. There's a very broad spread in where these measurements are. Here represents a very precise SE, so you can either say precise or you can say that there's high precision. Same thing, if I could spell P-R-C-I-S-I-O-N. However, this is not accurate. The measurements are very close to each other, yet they're far from the true value. Here's where we really want to be. This indicates where we have a high level of precision and a high level of accuracy. The measurements are very close to each other, and they're all very close to the true value. Here, if we did the average, it would be somewhere in here. So by either on average or simply by measuring a single measurement or looking at a single measurement, this is not accurate. And there's a large spread, so this is not precise. When we consume a measurement, use a measured number in our calculations, we want to appreciate that there's 3 bits of information that are conveyed in that measurement. The magnitude of the size of that property, which corresponds to some number. There has to be a unit, or occasionally there's more than one unit associated with that, and some level of uncertainty. And this needs to be communicated via the number of significant figures. And when we use measurements correctly in a calculation, we recognize that the measurements are not just numbers. They always contain some inherent error, and that error may be propagated through the calculations and affect the quality of our calculation. And whenever we report an answer, we have to make sure we have the appropriate units. quickly to summarize, significant figures are all the digits that are known in a measurement plus one uncertain digit, and that's going to be the last digit given. The last digit is estimated. Typically we either read between the lines, or if it's a display, we simply recognize that that last digit is uncertain. The number of significant figures vary depending on the measuring device and the skill of the operator, but in general, the greater the number of sig figs, the better, the more reliable the measurement is thought to be. To calculate or determine the number of sig figs in a measured number, we apply the following four rules. For example, if 137 kilograms contains 3 sig figs, because each of the numbers 1 to 9 count as significant. If we had 104.3 meters long, this 0 is a captive 0, so it would count as significant. So we'd have 1, 2, 3, 4 significant figures. Leading zeros. Leading zeros are there simply to hold that decimal place open. So if we measured something on an analytical balance that didn't weigh very much, let's say we had 0.0034 grams, these zeros are leading zeros and do not count as sig figs, so only the 3 and the 4 would count as sig figs. This number would have 2 sig figs. Zeros, trailing zeros, are the zeros at the end of numbers. Now they're treated two different ways. The zeros at the end of the number with a decimal point are always considered significant. For example, 40.0 grams is going to correspond to 3 sig figs, because each of these zeros are significant. This is a number that has a decimal point, so all the trailing zeros are significant. An ambiguous situation is, say we have a situation where we have 500 milliliters of a substance. Now we don't know whether or not these trailing zeros are meant to be significant because there's no decimal point. If we wanted to indicate the measurement of 500 milliliters with, let's say, 3 sig figs, we could write this as, say, 500 decimal point milliliters, because that would make these zeros count as significant. Or preferentially, we would write 5.00 times 10 to the second milliliters. So if we use scientific notation, we know that all the digits in this coefficient are going to be significant. If we had to write 500 milliliters with 1 sig fig, the only way we could possibly do that is using scientific notation. This would be 5 times 10 to the second milliliters.